Okay, Liu Ying, can you hear me? Can you hear me? Can you see the screen, the Geometer Sketchpad screen? Okay, can hear and can see the screen, both, both. Yes, both, okay. Uh, 3 minutes more. You just wait for another 3 minutes. At 4, we start. 2 minutes more. Okay, okay, right. Uh, Last week, someone asked me about this PNjunction. Before I start, once again, can you hear me? Because it is raining outside. Can you hear me or not? Hello?
Hello, sir.
Can you hear me or not? Because it's raining outside.
Yes, sir, can hear you.
Can, if not, I'm going to close the window.
No, sir,
Okay,
can hear you, sir.
okay, right. So we are going to start with this diode. Okay. Now, the diode, you need to know about the orientation. That is the terminal, the positive terminal and the negative terminal with respect to the p-type and n-type semiconductor. Okay, so p-type and n-type semiconductor is the internal structure of the diode, whereas the terminal, the external terminal, is the anode and the cathode. Is the way how you connect it to the uh, PN junction or our transistor diode. I need to mention transistor diode because diode, you can also have the vacuum tube diode. In the olden days, we have the bulb type of diode. Okay, of course, that type of diode we no longer using it. And Regarding this transistor I mean this PN junction type of diode, uh, you need you need to know that they can only use under very small current. Okay, you don't expect to run this diode, this PN junction diode, using our normal current and our normal voltage from the 3-pin plug. Okay, 3-pin plug is a 220 240 volts, and this type of voltage will destroy the diode. Whether you are putting it in a forward bias or reverse bias, it will destroy the diode. Too high a voltage, too high a current will destroy the diode. So you have to know like that. Whether in either direction, it will destroy the diode. It will destroy the very basic structure of the silicon and the. Wait, Ranga, stop drawing on the screen. Okay. Right. So you bear in mind that these diode, they only allow a small voltage and a small amount of current to flow. Okay, right. So we come back to this structure of the diode. Okay, the diode consists of a p-type semiconductor and an n-type semiconductor. Now, this p-type semiconductor can either be silicon or germanium, which is doped with uh, pentavalent, no, trivalent, okay, which is doped with a trivalent, uh, how is it? Trivalent element, right? It's kind of something like your arsenic lah and things like that. Okay, so we don't talk about the actual element that is used to construct this diode. So we know that there's one p-type semiconductor. This p-type of semiconductor is doped in such a way that there is always a lot of holes there. Holes, they are just positive charge. Okay. Now there's another type of semiconductor which is the N-type, and this N-type is doped in such a way that they produce a lot of free electrons. So when we join these two type of semiconductor together, then something will happen. Something will happen. Now what is going to happen is these electrons from the initially, before anything happened, you just join the two of them together, then they are neutral. They are not neither positively charged nor negatively charged. Overall, both of them, they are neutral. They are not charged. Now, when you join the two together, the P and N together, then something start to happen, because this P is rich in positive charge or holes, and the N is rich in electrons, free electrons. The electrons will migrate at the junction there, at the border there. The electrons will migrate over to the P side, okay, to fill up the holes there. Now, as a result, the P side will have a certain amount of negative charge, and the N type, on the N side of the junction means the place where they meet, will have some positive charge, but overall they are still neutral. Now we say that this is in an unbiased state. Unbiased, that means they are neither forward biased nor reverse biased. Okay, so they are in an unbiased state. Now the reason why it's unbiased is because they are not connected to any external potential difference. They are not connected to any external voltage, right? So in this state here, now you see my mouse here, in this state, where the electron migrate over to the positive side, and the positive charge migrate over to the negative side. Now in this state, they are at the unbiased state before you put any connect any voltage to it. Okay, now the size of this layer here, okay, the size of this layer depends on the type of element we use. Okay, the type of element we use. Who is this BBM92392? Ganga, you know her or not?
Kisanya, sir.
Okay, Kishania, never mind. If there's anybody you don't know, you tell me, I just kick them out. Okay, right.
Sir, sorry, sir, for just now scribbling there. Accidentally pressed, sir.
Never mind. It's okay. Now, if don't because I don't want anybody come in then disturb, then they're not inside our group. Because now I didn't put any room there to enable you to come in. No need my approval. But if you see some strangers there, you better tell me. Okay, right. So now this layer here, where there is a migration of charge, is called the depletion zone or the depletion layer, where there's a movement of charge from this side to that side to this side. Now this zone here, overall they are still neutral. Overall they are still neutral because the number of charges here and number of charges they are the same. So overall they are still neutral. Now, however, this migration of charge from the positive side to from the P type to the N side and from the N side to the P type to the P side will set up a potential difference within the diode itself. Okay, because there's a positive side here, there's a negative side here, there will be a small potential difference there in its natural state, undisturbed state. Undisturbed means I have not connected to any external voltage yet. So in this undisturbed stage or the unbiased state, there is a small potential difference within the diode itself. Okay or not? And this potential difference is called the junction diode. It's called the junction diode. And this junction diode here, that means the amount of charge that migrate from one side to another, it depends on the type of element. Now, if it is germanium, it will set up a junction diode of 0.1 volt. If it is silicon, it will set up a potential difference of 0.7 volts. So this will occur naturally, right? But if you look at the thing as overall, they are not charged, they are neutral because the number here and number here, they are the same. They balance one another. But within that region, within that zone, there is a potential difference. Okay, somewhere here no potential difference, here no potential difference, but here there will be a potential difference, right? Okay, now so far any question or not? So far any question?
Sir, the migrated charges are the electrons and the holes.
Actually, the electrons and the holes, they are actually the same thing, but they are opposite side of the coin. They are just opposite side of the coin. When you remove away the positive charge, then there will be a hole there, right? Well, actually the hole, then you say whether, hey, is the hole moving? How can the hole move over to the other side? Now, let's say, for example, this side we have holes, okay? This side we have holes, this side we have electrons. Now, when the electrons go and fill up the holes this side, take the electron, fill up hole, so they are all holes over the other side, right? So that means when the migration of electron to this side, there will holes will appear here. The holes don't actually move from one side to another. The hole will not move from one side to another. But then when you move the electron, there appear to be holes here. But initially the hole is on this side. But how come it appear on this side? So we say that the positive charge move over to the other side. But actually they are the two sides of a coin. Okay or not? So far okay or not?
So, sir, the potential difference is formed because of some electrons at the end P type and some holes at the N type.
No, no, no. The potential difference is due to the migration of electrons. From this side, the electrons move to this side. Then all the holes start to appear on the other side. So that means there is a potential difference there. Now this region, they are no longer neutral. Let's say I put a test charge. You remember the first day you learn electricity, you put a test charge there. Now if I put a positive test charge there, then the positive test charge will move from the positive side to the negative side. So it means that there is actually a potential difference within the diode itself. However, if you put it over here, they are all neutral. They are all neutral. This region is neutral. There's no electric field here. There's no electric field here. But there is an electric field at the junction there. And this electric field is due to the migration of the electrons to the other side. And they are very small potential difference only. You don't imagine that, wow, this is a very big potential difference, wow, the charges will be flying all over. No, not like that. So you will set up a small potential difference there within that junction there, that area around the junction there, and it's very small. It's 0.1 volt for germanium, 0.7 volts for silicon. Any more question?
Thank you, sir.
No, no. Right. So if you cannot imagine, then you try to think of this potential junction voltage, right, as a spring, a spring. You know the people that do the workout one, the bull worker or whatever they call the spring, then you stretch the spring like that. Then you compress back the spring like that, something like that. So imagine it as a spring, okay? So at this state here, at the unbiased state here, you just pull it a little bit, pull it a bit. When you pull it a little bit, the charge cannot flow through. You see, you take the spring, you pull out, then they are actually blocking the flow of charge from this terminal here, from the anode to the cathode. So it will be blocking that the flow of charge there. So you stretch out the spring so like you tahan the electron from moving from one side to another. So the analogy is a stretched spring. Okay, okay, now this one. At this state, we can draw analogy of a depletion layer to an uncompressed spring at its natural length. So that means this spring is already like that, open up like that, right? So if you want the electron to go through, you have to compress the spring, right? You have to compress the spring until everything become very thin, then the electron can go through. Okay or not okay? So, but of course, this is an analogy. Uh, it is not, how to say, it's not a physical spring inside there. So you imagine it's as a spring like that. So you want to go through, you cannot go through. You have to compress the spring before you can go through. Okay, so anything you want to ask? If no, then we go on to the next one. Next one, next page. Okay, next page. Okay, now, where is it? Now when when the diode is in an unbiased state, that means when you have uh, electron move over to the other side and leave behind the holes here, then now we are going to apply an external voltage to it. So this external voltage, you take note, this is the P side. I connect it to the positive terminal of the external voltage. And this is the N side. I connect it to the negative terminal, connect it to the negative terminal. So this side is known as the anode, this side is known as the cathode. And the electron, sorry, our conventional current will flow from positive to negative. The electrons will flow from negative to positive. So far, any question or not? The conventional current. Have you learned about the conventional current and the flow of electrons? Yes or no?
Yes, sir.
Okay, so you know what is conventional current and what is the flow of electron. Conventional current is the flow of positive charge, or maybe the movement of holes, right? The movement of holes, and the other one is opposite to our conventional current is the flow of electrons. The electrons, they move, okay? So current can be seen as a conventional current and the flow of electrons. Okay, right. Now, when the positive charge is connected to the positive terminal of the battery or of the battery, let's say battery, and the negative, the N side of the semiconductor is connected to the negative side, the negative terminal of the battery. So this connection is called the forward bias. Forward bias. Okay. Now, if you look at the external voltage, positive, negative. So we are supposed, the positive charge is supposed to flow from this positive side to the negative side. Okay, but this, you want to flow from this side, the positive side to the negative side, you are actually blocked. Okay, blocked by the depletion, by the depletion layer, the depletion zone here. So if you put the positive here and you put the negative here, actually this layer here is blocking the flow of the positive charge from the P side to the N side. Now, in order for it to flow, you must exert a greater potential difference. greater than the voltage here. So once you exert a greater voltage than the junction voltage, then you can actually overcome this depletion layer, and the charge can easily flow across from the P side. The positive charge can flow from the P side to the N side. So over here, okay, before this no, sorry, the conventional current can flow like that, they have to overcome the depletion layer, the depletion zone. Okay, you see the analogy here. Now the depletion zone is like a spring like this, and when we apply a positive charge and a positive terminal over this side and a negative terminal on this side, we're actually pushing the depletion zone, pushing the negative charge back to the other side, pushing the positive charge back to the other side. So we're actually compressing, something like compressing the depletion zone or the depletion layer. So compress it. But if you apply a small voltage, it is not enough, let's say less than 0.1 for germanium, less than 0.1, it's not enough to overcome the energy is not enough to overcome this depletion zone. You're not able to push it back altogether. So it's just like push it back a little bit. As you increase the voltage, the positive side, negative side, right? Positive side here, negative side. As you increase the voltage, more voltage will try to push them back, push the electron back, and you actually compressing the depletion layer thinner and thinner. So when the external voltage is equal to the junction voltage, then yeah, you have overcome the junction voltage already. Anything more than that will allow the current to flow through. So far, any question? So far, any question? So if you don't understand what is happening inside the PN junction here, you just look at the analogy here. The analogy is a spring. The spring is actually the junction voltage. It is in this state, stretch out in this stage. So your external voltage is pushing it back more and more and more until your junction voltage becomes zero, and you push some more, the current will go through. Okay or not okay? Any questions so far? Ganga, any question?
No, sir.
No. So this is called forward bias. Forward bias will allow the current to flow through, but you have to overcome the junction voltage first. Forward bias. Okay. Now, if you look at the symbol of a diode, it's actually putting an arrow pointing from the anode to the cathode. Can you see like that? This arrow here, this is the arrowhead. They are pointing from the anode to the cathode. Now, actually, this is the forward bias state, in the forward bias state. Okay, the positive side is connected to the P type. The negative side is connected to the N type. Now, this is the forward bias. You can see that the arrow there. Now, the arrow is the direction of the conventional current, not the direction of electron. So it's like that. So if you can overcome the junction voltage, then they can go through. Now, this line here, this line here shows that if your current is coming from, your conventional current is coming from this side, it is blocked. They're coming from this side, the line there means it's blocked. Now this arrow here means that they can go through. The arrow means if you're coming from the arrow side, you can go through. So this one is in forward bias, this one is the reverse bias. So okay, so this is the structure, and this is the symbol. Okay, the symbol will also tell you how the position of the P type and the position of the N type. Okay, right. So coming back to this, forward bias means you connect the positive to the P type, the negative terminal to the N type. And if the voltage is more than the junction voltage, the current will flow through. because you are actually compressing the depletion zone until the depletion zone no more than the positive charge can flow through. I mean, I'm talking about the conventional current. Okay, so if no question, then we go on to the reverse bias. Now, okay, now this is the depletion zone. Let's say we don't have the positive and negative terminal, and we just have this in an unbiased state. Okay, in an unbiased state, there will be a depletion zone here, right? Now, this depletion zone consists of over here, you look over here, it consists of negative. Can you see the negative sign there? Negative charge on the P side and the positive charge on the N side. So this is called the unbiased state. Okay, unbiased state. Now, if you connect the positive on this side to the P side and the negative to the N type, then you will actually compress the spring and cause them to become smaller and smaller. Now, however, if you reverse the terminal, okay, if you connect, you see this is the negative terminal. The negative terminal is connected to the P type, and the positive terminal is connected to the N type. Now, do you expect the external potential difference to push? No. But if you reverse the polarity, the terminal, the positive and negative terminal, you don't expect them to exert the same type of pressure that is compressing them. If in the forward bias, you are actually compressing them, in the reverse bias, you are actually stretching the spring. So what the external potential difference do to this depletion zone is actually they are pulling them and making them thicker and thicker. By pulling them means you are actually asking more electrons to flow to this side and create more holes on the other side when the external terminal is reversed. So the reverse force is happening, right? The reverse force, instead of compressing it, you're actually stretching it. So if you look at the diagram here, right, the analogy here is that when you apply the negative terminal here and the positive terminal a little bit lah, so you're actually stretching it, making the layer thicker. Apply more potential difference and it becomes thicker and thicker until you apply a certain voltage, very high voltage. You look at this graph here. Okay, you look at this graph here. So when you apply the voltage in the positive direction, in the forward bias direction, this is the forward bias, forward bias. So the current will not flow until you exceed the junction voltage. Then the current will start to flow. However, if you apply it in the opposite direction like this, you are actually making the depletion zone bigger and bigger. So you apply negative 10, negative 20, negative 30, negative 40 until how many? 50, 50 some, 55, okay. Let's say 55. Still the current cannot flow because you are actually pulling them in the opposite direction. So the current will not flow through. But if you apply very big voltage like 70 or 80 volts, then the current suddenly can flow through. Now, this is called the avalanche breakdown. This is the avalanche breakdown, whereby the internal structure of those silicon or germanium, if you are using germanium, is destroyed by the external voltage, because this external voltage provide a lot of energy. So they will actually pull out all the electrons, and create all the holes in every atom inside, almost all the atom, silicon atom and the germanium atom inside, okay, inside this diode. So as a result, once it's destroyed, the current can flow through lah. So if it's around 60 to 70 volts in the opposite direction, in the reverse direction, then they can flow through. But by that time, that PN, that diode is useless already. That diode is it cannot be used to to cause the current to flow in a particular direction anymore. They can flow anywhere they like. They no longer offer any stop to the current. Now, if you remember, the diode is actually to make the current flow in one direction. Now, if both directions also can flow because of the destroy the structure of the atom, the structure of atom is destroyed, then it cannot no longer can function as a diode anymore. Any question?
So in the diagram 3, right, so on the reverse bias
This one,
for
huh?
the
Yes.
why is it stated the negative ion and positive ion, sir?
Actually they can you can call it electrons and holes, because let's say the electrons lah, the electron, let's say this is the silicon atom. So when the electron move into this silicon atom, this silicon atom become negatively charged, so it becomes a negative ion. Whereas the other one, let's say the silicon atom on the other side, and when one electron leaves this silicon atom, so this silicon atom becomes a positive ion. That is what they mean. Okay, now, so
Yeah, okay, sir.
you
Thank you,
don't
sir.
worry about the actual structure inside this PN junction there. You think about the direction, how they prevent the current flow. If in this direction you're actually stretching it, opposite direction you're compressing it, where how you compress, which one, how you should connect the positive and negative. That is more on the physics side. Whereas the structure of the atom is more on the chemistry side. Chemistry, they also study these things. Right? Okay. Any more question? If I think this thing I already put inside the Google there. So then the recording, I will just post it. This whole thing, the recording, I post it inside the Google Classroom, the link to the video. Any question? Any more question? Kishania, Ganga, how many girls? Farah, Farish, not Farah. Farah and Farish. Yes, Farah and Farish. Any question? Where is the chat?
No, sir.
No, no, no question. So if no question, then that's all lah. I'm going to upload this into your Google Classroom. You can read all these the words there. Okay, then we should stop sharing. Then we should stop recording.